أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Welcome back, all. This is another series of lectures for the power dividers and the additional couplers. This will cover the entire chapter 7. In these lectures of this few series of lectures, we will learn about how the power dividers and the directional couplers has been designed and what is their functionality and what is their application. Basically, these two devices, the power dividers and directional couplers, are very useful devices and is been in use by the designers for ages. Basically, these two devices are used in the transceivers, like the receivers front ends, transmitter front ends, and so on and so forth. So let's go to our slides. Here there are some photos of the power dividers and combiners. I will tell you why we are telling it divider and combiners also. And then there is another device, directional couplers. These are the power dividers, which is, you see that there are in one, this is a resistive power divider. We will learn about it from the this is which works from DC to 14 around 14 gigahertz, and from Agilent company, which is very renowned company. This power divider actually takes one input and divides into two. The rating is, I don't think we can see the rating here. Usually they are like 6 dB or 3 dB couplers, dividers and combiners. So if this is 3 dB, or if this is 3 dB, if we say it's a 3 dB divider, then the power input, let's say that you give 1 watt here, and then divided, split into two, half a watt and half a watt. So 3 dB divider. In similar way, not only two way we can split in multiple ways like this. Let's say this is the input, and there are 4 different outputs, so it will divide the power into 4 different output. Remember one thing, these two, all of the ports are actually, if you add all the port power, then it have to be, and it is actually equal to the input power. In similar way, if as this one actually it splits the power with two different same frequency signal. If you give different frequency or same frequency signal here with the different power, it will combine this power and give you one output. So that's why we call it divider, and also we call it combiner. Like this one also, let's say we have 4 different signals here, and then when we give feed and we get a signal back out, which is a combination of different frequencies or a single frequency different signal, but the power will be 1, 2, 3, 4. We add them, and together the power will come out from here. So the power will be this plus this plus this plus this is equal to this one. Similarly, this and this. Let's say if they have 1.2 watt here and they have 0.8 watt here, so it will give us 2 watt. However, there are some insertion loss here. During the insertion, there will be some losses. So we'll not get exactly for sure, but theoretically it is like this. Um, as we can combine and we can divide here, we need sometimes we realize that we can couple the power what is input we're giving input. Mm. Sometimes when we try to receive something, it have some problem, they have some isolation problem, so it goes here also. But if we have an input here, if it's supposed to go here, it's desirable. If it goes here, it's not desirable. That is the reason sometimes we need uh, another device which inputs the signal, but uh, which can divide the signal, but when it inputs the signal, it doesn't go to the another input port. Hmm. So due to this problem, the directional coupler actually invented. Well, this is usually a 3 to 4 port network, but usually we have a 4 port directional coupler, very widely used and available in the market, where we take an input here and then this is the output through port. But some of the power, this is called a coupling port. Let me start from the beginning. This is input port 1 and this is output port. So we're at the desired frequency is if this is input and this is the output. And this is, we call it coupling port, and this is we call isolation ports. How we use it actually, that if we have an input here, then that all the output come out from here. But there is a certain amount of power will be at this port splitted here with the coupling. Let's say we design a 20 dB coupler, means uh, a 20 dB power, it's like minus 20 dBm or something like this power. Let's say we put 1 dBm, 0 dBm here, so minus 20 dBm here, and the rest of the power will go through this port. And it is desirable that there will be no power coming here. In the similar way, if a power comes here, then there is no power will be coming here, and all the power will be going through this port. So that's how we actually can isolate this port from here and then couple this with this one and isolate this port from here. That's why these directional couplers are very effective, and this is a multifunctional device. So this is a hybrid type and this is a microstrip type, where this is input, this is the coupling port, this is isolation port, and this is the through port, we call it through port. So this is the basic idea actually, and the construction of the real practical devices of the power divider and combiners and directional couplers. But well, this course actually cover how, not most of the theories for sure, because we doesn't go to the theories mostly, but for sure some theories needed to be explained to understand how these two devices, how they have designed. So we move on now. I just want to show you the application of these two different devices. This is a 2010 ultra wideband, means UWB means ultra wideband RFID reader circuit, where this reader actually reads the chipless tag for item tracking and identification, where this is a transmission antenna and this is a receiver antenna. You can check here, this one is a 10 dB directional coupler they have used. So when they generate a signal here with a VCO, we call it oscillator circuit, where we generate RF, and then when you input to the directional coupler, there is a coupling port to have the same signal at the mixture point here. So after that, we throw this one out to for the tag identification, and then when it reflects back, then we have some filters, power gain amplifiers, and everything. And then here you check there one LO is local oscillator VCO here. Here this device is called the divider. So here we divide into two parts, and then we mix with this coupler, and this same signal we mix it with here, and then the receive signal comes here, and then we mix together, and then we compare here for the identification. So now here you can see that what is the significance of the directional coupler and the power divider here. Directional coupler we can couple and we can throw, and there is isolation port. We don't need that now because we have two different antennas. If the single antenna, then we use this isolation port for our output, and then this directional with this power divider we again divided and then put into two different mixture, and then when we compare our intermediate signal, and then we compare here for our gain and phase detection. It looks like a complex RF circuit, but you don't need to go deep into it. I just wanted you to know where we use our directional coupler and power dividers. There are some features of this type of devices that a power divider or coupler both can do power division and power combination. So it can actually combine power, and also it can divide the power. Coupler divides with the coupling port, and power divider divides with the two different output port. This power divider and coupler can be 3-port and multi-port, and I show you already that power divider can be 3-port or multi-port, and coupler is usually 4-port, but they have 3-port and multi-port also. And there are some features what I told you, because there is a through port here. If you go here, this is called directivity. This between these two is called coupling, and this one called isolation. Later on we'll talk about it. So there are some features here, which is power division and combination. They can both power divide the power, and it can combine the power also. They can be 3 or multi-port networks, and there are some parameters we need to learn, which is coupling, directivity, and isolation. Okay, now for the classification, there are many actually, but we usually what we do, we bottom line it. We bottom line it into basic devices. These basic devices are actually two types: power divider and combiner have basically two types, which is junction T-junction power divider, and the other one is Wilkinson power divider. T-junction power divider have two type of two different branches of design, which is one is called lossless and another called resistive. Wilkinson power divider itself have some different subcategories, but usually we don't categorize it with different designs, because Wilkinson power divider can be from 3-port to multi-port. And for directional couplers, there are two types. One is quadrature hybrid couplers. There are ring couplers also, but we will not. This course we will not learn that about that one. There are actually many, but we just summarize into few basic designs. And So directional couplers have two two types of designs, which is quadrature hybrid couplers and coupled line directional couplers. Usually, these two devices, they are very familiar in the RF sections and RF generation units. The lossless For the T-junction power divider, the lossless types are actually loss-free. Means we consider that there will be no loss inside when there is input and output going on, and divides the power into desired ratio. However, when we try to get the output, the reflections are very high, which is goes back to the source, which is undesired. That I have already told you that reflection towards the source is undesired. So this is a drawback here. So to deal with this drawback, the resistive type uh, junction filter, power divider has been invented, which is a little bit lossy, but it's the input power with no theoretical reflection actually. So these problems with reflection has been solved by this one. However, a resistive means there will be losses, right? So usually when they try to divide the power, we get 1/4 of the input power. So half of the power in both of the, if we let's say we want to divide it into two splitting powers, then 1/4 of in one power in one, and another 1/4 will be in another port. So half of the power will be lost. So this is one more problem which needed to be solved. To resolve this issue, Wilkinson power divider has been invented, which is actually solve the both issues of loss free, which is a loss free, and it can equally divide, or it can divide in any other ratio. Let's say 1:2, 2:3, 3:6, 1:3, any into two different ports or multiple ports. And theoretically, there is no reflection, which is we call all the ports are matched. So let us go inside let's discuss about in terms of the S parameters, where we can see the three-port S parameters. All these are three-port S parameters. In all those three-port S parameters, this is parameter for the lossless power divider, this is for the resistive power divider, and this is for the Wilkinson power divider, where we can see, since this is S parameters are actually voltage dependent, so here we can see that this one means it actually takes the ratio 1:1, but only port 1 is matched because there is no reflection here. Since we know this is the reflection coefficients and these are the transmission coefficients, so this diagonal needed to be 0. If there is no undesired reflection we want, then there's supposed to be no value here. It all have to be 0, but there is no. Actually, we will derive this one and see why this is happening. So we can see there is 1/3 of the power is reflecting back, and here 2/3 of the power is reflecting back. It means this is a design which gives us a lot of reflection. So lossless power divider had this problem. To deal with this issue, resistive power has been invented. However, it solved the issue of the reflection, but the power will be 1/4 at the two junctions, because this is voltage. So voltage usually we convert into power and we need to square it, isn't it? So it means 1/4. So when it goes, we try to split it, it gives us some losses inside the power divider. However, to deal with the reflection, this is a good power divider. However, to deal with these two different issues, Wilkinson power dividers are actually designed where there is no reflection and the power has been divided equally. This is voltage, right? If this is voltage, so it means 0.707, or you can actually square it. If we square it, then you see half, right? Square it means the power. So if we square it, this is the half of the power, which can be split into two different uh, junctions of the split. So there is no reflection and it can equally split the power. So in terms of S parameter, actually, why I demonstrate this one, because at the end we will try to find out the S parameters. We'll not go so deep into this one. We will design it only. But there are, of course, some derivations, and this is a very, very long and tedious derivation where we will not go in Wilkinson power divider. However, these two we will try to derive and give you an idea how the things happens. So in terms of this, we have a very clear, in terms of actually S parameter, we have a clear differences between these three different design of power splitter. In the next video, we will start designing this tool, and we will see how these two um, uh, power divider can be designed.